In our last video, we derived the solution for free fall in a vacuum. And because of the assumptions, we had to accept a few limitations. The equation is a good model for small heights, but if we try to describe a cat on a parachute with it, the result would look like this. And cats in a vacuum don't have a long life expectancy anyhow. Lucky is not a fan of that. What we actually want is something like this. After some initial acceleration, the motion settles into a constant final speed, and the cat lands safely on the ground. So, what does the equation of motion look like for that? Welcome to Physics with Lucky. Today, we are talking about free fall with linear air resistance. If you look at the forces, you first see the constant gravitational force Fg acting downward. But with drag, an additional force appears, one that points exactly opposite to the direction of motion. This force grows as the speed increases, until the two forces cancel each other out and the speed stops increasing. So, we have the gravitational force Fg pointing downward and in addition the drag force Fd pointing upward. We already know Fg. That's mass times gravitational acceleration. But what does Fd look like? There are basically two models for Fd: linear drag and quadratic drag. Linear drag is proportional to the velocity v, but opposite to it. To describe how strong it is, we introduce a drag coefficient b, and the larger b is, the stronger the drag. With quadratic drag it's similar. Again, we have a force opposing the velocity v, hence the minus sign, and a coefficient, which for simplicity we'll also call b for now. But there's an extra factor of v. Because the drag grows quadratically with speed, you can't just write v squared. Because v is a vector. V squared would be a scalar product and would lose direction information. That's why we use the magnitude v. This captures the quadratic dependency while keeping the direction information. Both types of drag have different use cases. Linear drag works very well for small speeds and laminar motion, while quadratic drag gives better results for large speeds in turbulent motion. The first is used more for viscous media and very small objects, like fog droplets in air, and the second for humans, cars, or, well, cats. Since linear drag is a bit easier to handle at the beginning, and it already explains the core ideas really well, we'll start with that, even though it only applies to the parachuting cat in a very limited way. Alright, let's go. We use our one-dimensional coordinate system again, where the y-coordinate describes the height, we use Newtonian mechanics, and we consider a point-like object of mass m, that we drop from the height h. The gravitational acceleration is still constant, on Earth that is about 9.81 meters per second squared, and the only difference compared to the last video is that this time we do not ignore drag. Our starting point is again Newton's second law. The acceleration of our object is proportional to the sum of all forces acting, and the proportionality factor is the mass. Since all forces act only in the y direction, we can omit vector notation and write Newton's second law for the y component. Today, we introduce a new notation. The acceleration, which is the time derivative of the velocity, we will often write as v dot. Physicists like that because it keeps things compact. So whenever you see a dot on a quantity, it means the time derivative. So a is v dot. And we already discussed the forces, gravity and drag. The gravitational force is minus mg, and we model the drag force as minus bv. Lucky is pointing something out to me right now. In the equation, it may look as if both forces point downward, because both have a minus sign. But don't forget, during the fall, v points downward as well, so v is negative. If you insert an actual value for v, the minus signs cancel and minus bv becomes positive overall. So everything is consistent. If we divide both sides by m and rearrange a bit, we obtain our equation of motion. It already looks a bit more complicated than that without drag. It's a first-order linear differential equation. Yeah, let's solve it. And don't worry, it's actually fun. First, we want an equation for the velocity v as a function of time t. Before we start, we substitute the quotient m over b and call the new constant tau. Tau has units of seconds, so it's a time constant, and we'll see what that means in a moment. To solve the differential equation, we first multiply both sides by e to the power of t over tau. I know that looks completely arbitrary, but you'll see it works. Lucky gave me the tip. If you look closely, the left-hand side is the derivative of the term v times e to the power of t over tau. You just need the product rule. So we can replace the left-hand side by the time derivative of v times e to the power of t over tau. That makes the integration over time on the left-hand side trivial. Since derivative and integral cancel each other out, the solution is already inside the parentheses. On the right-hand side, we can pull the constant g out of the integral, and what remains is the integral of the exponential function plus an integration constant c. And integrating the exponential is straightforward. Now we divide by e to the power of t over tau again, and obtain v of t. Thanks for the tip, Lucky. The only thing left now is c. We determine c as usual using an initial condition. Remember, v at time t equals 0 is the initial velocity v0. If we set t equals 0, then e to the power of 0 is 1, and we get v0 equals minus g tau plus c. We solve for c and we are done. Now we insert c into v of t and we get our final equation of motion for the velocity. Even if it may not look like it yet, it's actually very elegant. We'll visualize it in a moment, but to make it really nice, we still need the terminal velocity. We said that during the fall, slowed down by drag, at some point a final speed is reached, that no longer changes because the drag force grows with increasing speed until it matches the gravitational force. That means eventually no net force acts on the falling object. We can therefore find this final speed by taking the limit of the velocity as t goes to infinity. So we insert v of t. G and tau are constants, so they don't change with time. But the exponential term with a negative exponent goes to 0 as t increases. That makes v0 plus g tau disappear. And what remains is minus g tau. Tau was m over b, so we get a nice expression for the terminal velocity that depends only on the constants describing the specific problem: gravitational acceleration, mass, and drag coefficient. Let's visualize this in a velocity time diagram. In our velocity equation, I replaced all minus g tau by the terminal velocity v unlimited. It's the same thing and it makes the equation much easier to read. The velocity is the terminal velocity plus the difference between initial velocity and terminal velocity. And that difference decays exponentially to 0. So the terminal velocity is the asymptote of v of t. But what does tau mean? We call tau the relaxation time of the system. It tells us how quickly v of t approaches the final speed, the terminal velocity. At time tau, the falling speed is about 63% of the terminal velocity, and after 3 relaxation times, it's already 95%. So after 3 tau, not much changes anymore. The force balance is almost reached. We still have one derivation left. We can say how fast the object is at any time t, but we still don't know what height it is at. We are missing y of t. We start again from the equation for v of t and write it directly as y dot. After all, v of t is the time derivative of the height. To compute y of t, we integrate again both sides over time t. The integral of y dot is y, and on the right we integrate term by term. The terminal velocity is a constant, so its integral is simply v unlimited t. And in the second term, we can pull the constant v0 minus v unlimited in front of the integral. What remains is the integral of the exponential function, and we already had that. It's tau times the exponential. Lucky is reminding me of the integration constant c, which of course has to be added. This already looks pretty good. We determine c again using an initial condition. The height y at time t equals 0 we called h. If we set t equals 0 in y of t, we get minus v0 minus v unlimited tau plus c. We solve for c. Now we insert this above and we obtain our final y of t. That's quite a long expression. At most we can factor out the difference of the velocity constants but it doesn't get any simpler. So this is our final solution for free fall with drag. If we undo the substitutions for v unlimited and tau, it looks like this, by the way. Kind of nice as well. Do you remember I said linear drag is much easier than quadratic drag? Hard to imagine it can get even more complicated. I assume you're pretty glad we started easy, but we will still do it, promise. Just not in this video. If you made it this far, you really must love this, so a like would mean a lot. Thank you. But there's one more thing. If drag disappears, meaning b goes to 0, then our solution should turn into the equation for free fall, shouldn't it? But if you look at it, that's anything but obvious. After expanding, you get lots of minus infinity and plus infinity, and you can't directly see how they might cancel. The way to resolve this is through the Taylor expansion of the exponential function. If you want more on Taylor series, we can do that. Write it in the comments. The Taylor series of e to the power of minus t over tau is 1 minus t over tau plus t squared over 2 times tau squared, and so on and so on. The higher terms are no longer interesting, because they contain higher and higher powers of tau in the denominator and therefore ultimately vanish. You'll see why in a second. 1 minus e to the power of minus t over tau is then 1 minus the series expansion. You can expand the bracket on the right, 1 minus 1 cancels, and the other terms change signs. We can now insert the result in place of the right bracket in our function y of t. If you multiply tau in front of the bracket with its content, 1 tau cancels from the denominators. If you look closely, you may already guess where this is going. Next we expand the two brackets. Minus g tau t and plus g tau t cancel, and if we now let tau go to infinity, all terms go to 0 that have tau in the denominator. This especially includes the higher order terms, which is why we wisely left them out already. And what remains is h plus v0t minus g over 2 times t squared. And there it is, the equation for free fall without drag. Nice. So our result is consistent. Lucky likes that very much. And here's Lucky, who is surely already thinking about our next video. It will probably be the quadratic drag, even if then only 3 people are interested. If you are one of them, feel free to reveal yourself in the comments.